Welcoming everybody to this week's materials seminar, and we're excited to have everybody online. Please mute yourself and you can indicate in the chat box if you have a question, and we'll go through all of your questions after Valeria's talk. And it's a great pleasure to welcome you, Valeria, as our speaker this week. And I'm happy to introduce you in case somebody is not familiar with who you are. You are currently at Trinity College, Dublin, that's in Ireland. And you are the chair, Valeria is the chair of nanomaterials and advanced microscopy at the School of Chemistry there at Trinity College in Dublin. And one thing that is really amazing, probably not only to me as a female, but also to hopefully all of our community, is that she is actually the first female chair in the School of Chemistry since the foundation in 1592. That's 1592 for all of the Americans that probably are not even familiar with schools and universities that are that old. And I think this is a great accomplishment, and I just love that we have somebody like you here to join us. So it's this is great. And
it took them
Valeria,
a long time. It took them a long time. I'm glad that it finally happened.
It took them a long time, yeah. So Valeria got her bachelor's in chemistry in Italy and her PhD actually in physics, also from Trinity College in Dublin. And she moved to Oxford. She just mentioned that briefly, and then she moved back to Trinity in 2012. She is very, very successful. She has won 6 European Research Council awards. Again, for the non-Europeans. Oh, 7 now. Oh, wow.
From last week.
Oh, my gosh. All right. Okay. 7 ERC grants. This is one of the biggest funding sources for European researchers, just to put that into perspective. So this is yeah, it's just amazing, blows me away. And she has been nominated as one of the world's most influential researchers of the past decade for the last 4 years, 2018, 19, 20, 21, and I'm sure 22 will be no different. Many awards. I'm actually, in the interest of time, I'm not going to name all of the awards. But yeah, we are very excited to have you here, Valeria. And please go ahead, share your screen. And we are very much looking forward to your talk on nanomaterials inks. And I believe there will be some work that you're showing also on vaccines. And this is a topic that is very close to my heart. So I am particularly excited. In case I didn't mention it, I'm very excited. Okay, take it away. Thank you so much for talking.
Thank you so much, Christina. First of all, for the invite, and then for this wonderful introduction. I'm truly thrilled to be here and have the chance to tell you a little bit about my research. And it's a pity that I can't be there in Arizona, but I promise a visit very soon, as possible. I need a bit of sunshine. In Ireland, we don't get many days of sunshine, I have to say. So any excuse would be great. So I'm going to go straight on to the topic of my talk. And well, I've been working on 2D nanomaterials since ever, basically. What we do in my group, we do everything from synthesis and purification. We do mainly liquid phase exfoliation, and then we seek applications, especially in the energy storage space, but not only. I will show you a few other things a little bit out of the box. So everything, I'll tell you a little bit about the evolution of my work, and leading on to the discussions of what is the latest work that I can tell you about. So everything, basically, my work with 2D materials started way back in 2008, when as a first-year postdoc, I basically developed a system, a methodology to select solvents that suitably exfoliated thick graphite flakes. So up until then, basically, soon after the discovery of graphene, the whole community started trying to exfoliate graphene, but there were not very many methods that allowed a scalable production. And I had been working at that stage for many, many years with carbon materials, carbon nanotubes mainly. So I had all the know-how, and basically I managed to develop a thermodynamic approach to select suitable solvents that were compatible with graphite in that case, and capable of basically taking the layers apart. And it all was based on matching the surface energy of the solvent you were using with the surface energy of the material you wanted to exfoliate, in this case graphite. After the selection of solvents, all you need is a little bit of a shake and stir. In this case, we gave we use sonochemistry, an ultrasonic bath, centrifuging, and all you were ending up with were very, very nice stable dispersions. Now I have this vial still in my lab as a momentum, like is a sort of a capture of time. And it's still there, it's still in the same condition. And basically, if you go look at the microscope, you will see that it's a very successful exfoliation. You get single layers, some multiple layers, but effectively was a very, very simple methodology that opened a huge amount of work that followed up, basically, because it opened up a lot of different possibilities of processing these materials that we didn't have before. A few years later, in 2014, a company based in the UK, Thomas Swan, came to us and basically bought the IP, the intellectual properties that we had developed on the liquid phase exfoliation of graphene, and they engaged with us on a project to upscale the production of graphene. And for doing that, we decided to go away from ultrasonication, because it has a lot of different issues to take into account. It's not a very good method to upscale, because there are very many variables that it's hard to control. So we went on to shear mixing, and we did the very, very first test. This is something that we shouldn't say in public, but basically the very first test of exfoliation using a shear mixer was with a kitchen blender. So we went to a shop, we bought a standard kitchen blender, and then we did use the usual method, solvents, graphite flakes, and we gave a little mix, and indeed we realized that we could exfoliate graphite with that method. Then we went on to the scientific way, and we bought a proper shear mixing tool, and effectively after a year of studies, we managed to find a way to maximize the yield, improve the yield of exfoliated material, and eventually this was the very, very first installation at Thomas Swan, where finally we could go from the 10 milliliters vials to a 3,000 liters container. And now they have even upscaled that, and graphite now can be exfoliated there down to graphene I think they can do 15,000 liters in half an hour. So this is a product that they now sell. Over the years, we have moved further. Of course, the family of 2D nanomaterials that we can exfoliate has grown exponentially. What we like about these materials is that, of course, here you see an image, a photo of some of the materials we have exfoliated in liquid phase. From the different colors, you can already see that they all have different optical properties. They would all have different band gaps. They would all have different mechanical properties. So for us is a major advantage. We can pick and choose the material that we want, using the properties that they have, and then make devices that really have the properties that we want. So in my lab, we really use 2D materials as proper building blocks, like Lego blocks, if you like these toys. I love them as a child, and we still use the same concept. So as you see in my group, basically we do this part, but then also we focused a lot, oops, I went back, on the characterization. And I will tell you a little bit more about that later, but basically I just want to go and show you some example of intriguing research that we have developed. So black phosphorus was one of the materials that we managed to exfoliate by liquid phase. And this is a very intriguing 2D material, very interesting. Nevertheless, let's say the interest on this material has been dumped a bit, especially due to the instability. The fact that it's very unstable in air, and it degrades, it's oxidizing quite quickly. So what we discovered a few years ago was that, in fact, we could use the same liquid phase exfoliation methodology to pick and choose compatible solvents. And these solvents had the overall result, again, of exfoliating it successfully. And here you can see some high resolution TEM work that shows that indeed the atomic resolution of it shows that it's pristine. There are no defects, and it's quite structurally pristine. What we showed was that the exfoliation was quite successful. We could get, of course, as in any other liquid phase exfoliation methodology, a sort of distribution of different thicknesses, mostly centered at about 8 to 10 layers with the standard exfoliation methodology. And the interesting thing was that in some special solvents like NMP, normal methylpyrrolidone, CHP, we found that really the solvent had an added value. Not only the solvent was managing to exfoliate the black phosphorus, but at the same time was sort of forming a sort of protective layer that really protected the exfoliated material from oxidation. For example, here there is a sort of time series of the same black phosphorus flake, fresh as exfoliated, and then again looked after 3 days, and then 16 days. You can see appreciable degradation after 16 days, but let's say up to 3 days and a week, actually, we couldn't see any sort of degradation whatsoever. So we kind of extended the shelf life of a material that would otherwise oxidize within hours. And interesting to see, actually, we did some in situ liquid cell TEM. So we basically have this holder where it's you have a silicon nitride electron transparent window here, there, and what you do is just you flow the liquid with the dispersion, in this case, in here, and then you use the electron microscope to see through and see what you get. And by doing that, we could actually see, let's hope this video plays, it never does, it's always misbehaving, but anyway, you would see that in some other solvents, you would see the flakes degrading almost within minutes. So you could actually see these flakes disappearing if this video was to play. I want to tell you a little story, actually, of an interesting, unexpected thing that happened in the lab with black phosphorus. I always I put it here as the beauty of the unexpected, because this is truly what a scientist does, appreciating the unexpected events. And for those of you who do electron microscopy, at high resolution, you know that especially when you deal with materials like this, which come in liquid, then what you need to do is just getting rid of the solvent. Otherwise, the electron beam would just break it up and it would just cause horrible contamination. So normally, to get this sort of images, what you do is you deposit the sample onto a TEM grid, and then what we do a baking. Just shuffle in an oven, temperature gradient, and we leave it there for a while. The unexpected was that we did the same with black phosphorus. We wanted to get atomic resolution imaging, especially of the edges. And what happened was that we left it there a few hours rather than a few minutes or half an hour, as we often do, because the solvent was quite thick and was not evaporating. So we decided to leave it there for just very, very long time. And what we realized when we put the sample back in the microscope was these very, very odd and strange lines building up. And they were all actually always parallel to each other. And they were kind of always starting from the edge of the carbon grid, the copper grid. At that stage, we were very, very horrified, actually. We didn't know what this was. We thought it was just something wrong with the sample. We prepared a huge amount of different samples, again, with the same procedure, and every time this happened. Then we decided to actually repeat the experiment in in situ TEM setup. So what we did, I stopped the video here. So what we did was exfoliate black phosphorus and then sprinkle some copper, metallic copper nanoparticles on it, as to reproduce these junctions, basically, where the black phosphorus was touching the copper grid of the TEM support. And then we increased the temperature up to 80 degrees Celsius. And what we found actually was very striking. Here I put some arrows. You can see these lines actually building up. I hope it's visible in this video. I will replay it again. So again, you can track these lines forming here. There's going to be another one starting from here and building up. This was extremely intriguing. So we were forming these lines when the temperature gradient was put in place. And these lines were always starting from this copper that we had purposely sprinkled onto the black phosphorus flakes. So we went to the aberration corrected stem, and we were amazed to see these lines actually being so regular. So this is you can see here the black phosphorus steps. So here you have a monolayer, 2 layers, and here you have it a little bit thicker. And what was beautiful to see was how structurally perfect these lines were. I'm going to zoom in, and you're going to see what the repetition of the unit cells here, how structured that is. And this was going on and on and on until the end of the flake, where the flake was finishing. So this was extremely surprising. So we were actually forming parallel lines of a metallic atomic species, in this case copper, on black phosphorus, which was quite unexpected. Again, we did all sorts of structural characterization on these lines. Here is these two atomic, these copper lines seen from 2 different asymmetry directions. Here you have a projection of a width of 4.3 nanometers, here a projection of 0.36 nanometer. Again, astonishing is how regular this structure is. So we did some yields characterization, and basically there was absolutely no doubt that this was actually metallic copper building up as wires along the black phosphorus structure. We didn't see any oxygen. There was no oxide being formed. It was copper on phosphorus, nothing else to see there. So we partnered with our colleagues who do DFT, and they basically helped us a lot in computing what was the most stable structure, understanding what was going on there. And basically what we understood was the structures effectively were only observed when they were built along only one direction, 0 direction, and never we experience any other growth from any other direction. So it was always growing from these grooves in the structure of the black phosphorus. So it was the black phosphorus really templating this growth across these grooves here. And we also realized from DFT that copper atoms were diffusing with a very, very low energy barrier, about 0.14 eV. And I think the most interesting finding, which we are now pursuing from devising perspective, is that any structure that at the end was stable, was deemed stable, was always metallic. So this was a huge advantage. And so this was something extremely unexpected. And this is something that, again, has given us a very, very nice twist. And we are in the process of using this for templating devices, because it gives us some unique opportunities to have really a 2-line thick metallic wire being able to be built on black phosphorus. And here I introduce a different class of 2D systems that actually Christina loves as well. We share the love for this class of materials. For those of you who have not come across MaxScenes or don't work with MaxScenes, so this is a wide class of, it's a family of materials. The ones I'm going to focus on are mainly titanium carbides and carbonitrides, so titanium C32, titanium CNT, and these are different types of 2D systems, in fact, because they start from max faces, which are they're layered but not held together by van der Waals forces as any other 2D system I showed you before. In this case, we etch away the middle layers, basically, and what we end up with is a sort of accordion type of structure after we do some aggressive etching of the initial precursor, the max face. And then once you do that, all you need to do is just a little handshake. In this case, the solvent is water, simple water, and all you need to do is just a little handshake, and here you have your nice and stable dispersion of MaxScenes. The beauty of this, you will see now getting onto the devices part of my talk. For us, the beauty of this has been the extreme easy processing that we are allowed with these materials. The advantage of being able to use water, for example, has opened up a lot of opportunities for us, and I will show you some of those. So this is the type of material that you get after a simple handshake in water, where you get extremely large flakes, all monolayers, and they are structurally actually very defect-free and very, very good. They are extremely conductive, electrically conductive, mechanically very robust. So for us, they really take a lot of boxes of processability and processes so that we can follow up with our applications. So the first application we did with MaxScenes, we partnered with Yuri Gogotsi on this, was really to use them to make transparent, flexible, symmetric, all solid state supercapacitors. So for those of you who work with supercaps, you would know that it's very, very easy to make a tiny supercap 1 centimeter by 1 centimeter. But it's very, very difficult to get a supercap of this size working. And what you see here is a fully assembled supercap where you have 2 electrodes, the electrolyte sandwiched together, current collectors, and it's very flexible, extremely transparent, 99% transparency. And here is overimposed onto my postdoc mobile phone. So it gave a very, very good electrochemical performance. Here you see the IV curves relative to these devices pushed up from 20 millivolts per second up to 500 millivolts per second. You see that there is no resistive behavior really. So that really gave us the confidence that this was a material that was indeed performing. And that allowed us to really explore applications that we had in mind, but we couldn't yet pursue because we always had been working with tricky solvents and non-volatile solvents that were compatible with other classes of 2D systems. So it was always tricky. So for example, in this case, we used a very simple methodology that used a 3D fused deposition metal printer to make stamps. And with this simple 3D printing, you can do stamps with any sort of geometry that you want. Of course, for supercapacitors, we love interdigitated geometries because they give us a lot of surface. But of course, you can be, you can set your imagination free and really design the devices that you like. And all you need to do at that stage is really dip the stamp into your solution, your maxing solution, and stamp away. So it's a very, very easy way to make prototypes in the blink of a second and then test them for any sort of property. And this is another step because what we did also was to print rolls. We basically did what the Babylonians did back in the 1800 before Christ. And they used to do this methodology to really print down their art. So they were doing their rolls, they were really inscribing their art on the rolls, and then they were just rolling away. And this is pretty much what we did, but with super caps and using maxing inks. And that really allowed us to really being able to print devices, several tens of devices in one go. So it's a very easy way to do fast prototyping. And we were indeed amazed by the fact that these devices printed in a blink of a second really worked extremely well. It started showing some resistive behavior of 100 millivolts per second, but let's say at low rate, they were working amazingly well. And this is something that it's extraordinary if you ask, because, well, all you have there, it's one roll, so it's one thin layer of material stamped on paper. That really gave us confidence to pursue things that were more sophisticated. And then we went, the most immediate development was on printing. We do a lot of printing in my group, and I'll show you just a few examples. So we developed a methodology to use maxing inks, both by extrusion printing and by inkjet printing. And then we do the normal device ink, we cast the electrolytes, and then we just characterize them as supercaps. So this is an example of some of the devices we printed by inkjet printing from organic solvents, normal methyl pyrrolidone, for example. The beauty of this is that, of course, you can make your interdigitated devices, but you can also have the freedom to build a little bit more complicated devices, like in series, in parallel. And we saw that, of course, we could use the fact that in this case, you are not limited only to make one pass, like it was for the stamping method, but we could really print many layers and build the thickness of our device. The beautiful thing is that if you track the conductivity, then we realize that by only printing for 5 passes, we could already achieve an extremely high conductivity. We reached about 3000 Siemens per centimeters, which was really, really good for the application we were seeking. And in this case, you could also see that the conductivity was not really affected by bending. So our devices have very, very high flexibility, and the conductivity was perfectly retained. This is again another example instead of the extrusion printed Maxings, this time from water, from a water base ink, no additives, nothing added, no stabilizer. The beauty of working with Maxings is that how easy it is to work with them. You don't need to add anything to get the right viscosity. The only thing we changed from here to here, it's really only the solvent, and the only reason for doing that is because by doing that we could tune the viscosity of the ink without adding any additive. So again, you can print by extrusion printing, again, the usual interdigitated devices with the geometries that you want. You can print more out of the box type of geometries. Bottom line, you can still get the very, very good performance. So only by 5 passes again of printing, we managed to get the resistance really down. And here is a conductivity as a function of the ink concentration that we obtained, and here is the type of conductivity that our inks achieved. In this video here, I also like to play it because you see how sturdy the devices are once they're printed. So in this case, we use the Scotch tape to kind of peel off a device after it was printed, and no matter how many times we did it, it really always came out clean. So we were not easily damaging our devices. They're quite sturdy and very good. So here is a little recap of how they behaved as supercaps. Here I show the aerial capacitance, and I compare that the aerial capacitance we achieved with our devices, the red and the light blue here, compared to other devices similar in thickness, size, that we could find in literature. And here is the Ragone plot, where it shows where this work performance lies as compared to other similar devices in the literature. So we could really achieve very, very good power density and a truly excellent energy density. Also, what we realized was that, again, bending of the device didn't compromise the performance. So here, some IV curves of the same device lying flat and then bent 60 degrees, 120 degrees, and so forth. This was recorded at 50 millivolts per second. More recently, we have moved all our expertise onto aerosol jet printing on textiles, and this is a very nice technology that we're using to put down inks by printing. It's very gentle on the inks, and it really gives us an added value of precision and lateral resolution that we can achieve. And we have tested several different types of textiles, going from cotton, polycotton, polyester, lycra, and all sorts of different fabrics. And the nice thing about printing is that you actually do not get shorting. You don't have to pre-treat the fabric with a polymeric coating, for example. So these are all devices that really have been printed down straight from Maxing inks on, in this case, this one here in this picture is cotton, I think. And again, tested as supercaps. And again, very, very good performance. Here, the light blue curve is 100 millivolts per second. The second one here is 50 millivolts per second, and you see that is a barely minimum resistive behavior there. We are also exploring 3D printing now because it gives us the advantage of building height. And of course, if we build height, we build higher thicknesses, we put down more materials as compared to the 2 layers, like the thin layers deposition that we achieve with inkjet printing, for example. So we can go on to the 3D printing era. And these are just some examples of the type of structures we can 3D print. The beautiful thing is that how sturdy these devices are, these shapes are, and the fact that we could really form them literally by printing and immediate evaporation of the solvent. Here is a cross-section of one of these devices showing the very, very nice high level of porosity that these 3D printed structures have. And we have compared the performance of 2D printed interdigitated supercaps based on MaXinks with 3D ones. And again, what we did here was just using the same interdigitated structure, but building pillars. And by simply doing that, we have achieved an aerial capacitance that it's about 97% higher than planar 2D devices. And this was just literally with 300 micron long peelers. More recently, we have also developed hydrogels based on MaXinks and PEDOT-PSS, a conductive polymer. And again, we have managed to find the right formula using additives such as dimethyl sulfoxide, sulfuric acid, and sodium L-ascorbate to really give the right consistency to the hydrogels. And the beautiful thing again is that with that we can 3D print these gels and into proper 3D structures. Here is an example of some of the devices that we can make, and we can achieve extremely high porosity and indeed a very very good performance, electrochemical performance. Another very, very nice type of processing that we have managed to make with MaXinks has been to combine it with this technology that is quite corroborated, using some sacrificial ceramic templates based on zinc oxide nanorods, and then literally coat these or dip or really dip them onto MaXinks solutions, and what you get is the MaXinks that start coating the nanorods, the zinc oxide nanorods. So all you need to do at that stage is to etch the zinc oxide nanorods away, and all you end up with are beautifully hollow structures made of MaXinks. The nice thing about these structures is that they're pretty much 99% air, and they're basically hollow, and we call them aeroMaXinks for this very reason. This is how light they are, and the good thing is that you can really build any sort of structure that you want, give them the shape that you want. And you also, because we're using them as super caps, we also wanted to increase the performance that we could obtain. So we added some compression steps in order to get more material down. So for a compression of about 40 times from here to here, we managed to control the density of the material. So here we went, we managed to control the density, and indeed we managed to get a very, very good electrochemical performance. So this is a very, very nice achievement, and also a very, very nice and stable performance. So before finishing off and telling you a bit more about the very latest results, I would like to also show you what we have done with MaXinks with batteries, in batteries application. Also far, I've been focusing on supercaps, and we have actually partnered with one of our industrial partners, Nokia Bell Labs, who came to us with a very, very interesting question. They wanted to develop anodes, battery anodes for lithium-ion batteries based on silicon. The problem there, as everyone knows, working with silicon nanoparticles for battery application, is that when you charge and discharge the anode material, then you actually also have a volumetric expansion and then compression of about 400 times. So the volume really changes drastically. And these cause cracking and then eventually pulverization after a few cycles. And despite silicon being a very, very good anodic material for lithium-ion batteries for its theoretical capacitance, then it's been really not a pursued strategy for the battery field because of this very problem. So what we have done is we have added basically MaXenes and made composites by simple slurry casting, which is the technique that the battery industry uses. And we basically managed to make sort of hybrid composites of silicon particles and MaXenes by slurry casting. And what we have seen is that actually the MaXenes were kind of forming this sort of 2D sheets or blankets of MaXenes surrounding the MaXene nanoparticles. And these really had two main advantages. One was giving mechanical robustness to the electrode. And then the second one was that it really gave the conductivity that the electrode needed to function properly. So this is actually an example of some of the composites that we obtained, not only with the silicon, we also tried on the cathode side. Here is with a conventional three-phase type of electrode. So NMC, cathodic material, polymeric additive, and carbon black to increase the conductivity. And here you can see that already 288 microns, the film, the electrode was starting to crumble. Basically, we were achieving a sort of a critical cracking thickness above which the electrode really doesn't support anymore the work it's supposed to do. In our case, we didn't need to add any polymeric binder. We, of course, use MaXenes also as conductive agent. So we basically combined our electrode materials with MaXenes, and we could achieve record thickness for our electrodes. And this was unheard of because, of course, the higher is the thickness of the electrode material, the higher is the performance of the battery. And indeed, we could see that by using MaXenes, we could already by adding 30% of MaXenes, we could improve the conductivity between 250 times and 1,200 times, depending on which type of silicon we were using. And we also improved the mechanical performance of the electrode. So the tensile toughness was improved of about 15 to 40 times, again, depending on the type of silicon we were using. We could indeed achieve very, very high aerial capacitance. We achieved 12 milliamps per hour per centimeter square. And this really opened up a lot of the nice applications. And now we have patented this work, and Nokia Bell Labs is going ahead with this. But this is a very nice graph where I show the aerial capacitance as a function of the active material. And here you see actually the performance of our electrodes based on MaXenes and silicon versus the traditional battery that you find on the market, which can achieve traditionally about 40 milliamps hour per centimeter square. So we could achieve high mass loading and delivering very high aerial capacitance. So before finishing off, I would like to tell you a little bit about some of the latest things that we have been seeking in my group. And we've been playing around with MaXenes, again, making hydrogels with polyacrylic acid and calcium carbonate to really form very nice hydrogels to be used for MI shielding. What is nice about these hydrogels is how stretchable, malleable, and self-healable they are. So these are some examples, and also the high porosity that we get. For example, here is, you can see how self-healable they are. You just need to join two pieces of this, and then you just they self-heal. And here is actually the self-healing happening when on a simple when you put contacts down. Here it's one stretched composite, then you cut it down and you bifurcate it and you break the circuit, and then it self-heals within seconds. What is nice is that you can actually give it the shape of the material you want to shield. And this has been a great advantage, because one of the things we saw that really works for this material is how we can shield radiation. So, for example, here is the radiation of in the terahertz domain of an unshielded signal. Here you can see that already after adding 6.5% of maxine in this hydrogel, you can actually shield most of the radiation. And with 8.5% of maxines, you've actually completely shielded the terahertz spectrum. So this was quite promising. We believe that this shielding comes really from this beautiful porosity that we get. So the radiation gets in, and then it gets dissipated, gets reflected several times into the cavities, and then eventually gets dissipated, and the transmitted waves are really dimmed down. The nice thing as well is that these hydrogels are conductive, and we've also been using this to actually track how the resistivity can change when we stretch them, and when we mechanically give the formation to these devices. And we've used this to actually as sensors, as motion sensors. So here, for example, there is a piece of hydrogel mounted on the finger of my postdoc, and you can detect all the phases of bending. Here is on the arm, and you can detect the bending of the arm. Here is on his throat, and you can detect swallowing, all the different phases of swallowing. Here is in his forearm, and the forehand, and you can actually see the frowning of his as an expression, and there you go. And then you can also drop water droplets and detect how they impact the surface, or you can also write on these hydrogels, and here we wrote down the word okay, no, and yes, and you can really see all the differences. Last but not least, of course, we have pursued printing, because these are very, very easy to work with. So we have managed to extrude print hydrogels. And this is, again, very, very exciting, because we can start printing down materials, shielding materials with any shape or any geometry that we really need, that is conforming well to the object we need to shield. Last but not least, I will give you a few examples of partnership with industry, where we have used 2D MateriAlZ inks for solving their problems. So this is a work that we developed for Lego, where they wanted us to develop conductive coatings for very thin conductive coatings for their Lego blocks. Their interest is in making the Lego blocks coming to life, being programmable and having them smart. And actually they were looking for this. They came to the right group, and we managed to actually develop conductive inks, which are transparent enough to actually keep white Lego blocks white. And this is another project that we developed with a company, Grundfos, who wanted us to develop hydrophobic surfaces for their applications, which is they make pumps actually, and they wanted surfaces to be coated and being made completely hydrophobic. And then again, we could simply develop a spray method of some 2D materials, and we really achieved what they wanted in a very easy and cheap way. Another application of 2D inks was on heat dissipation. A Formula One company that I cannot be named, unfortunately, I cannot disclose their name, came to us with a very, very specific problem. Apparently in the Formula one of the problems is that the tires need to get to the right temperature, to the ideal temperature as soon as possible. So what they want is to be able to dissipate the heat that it's forming at the rim and to dissipate it through the tires as soon as possible. This, even a fraction of a second, apparently can make a big difference when they do run for a qualification lap for a pole position. So they came to us with this interesting and intriguing problem, and we managed to find a way to coat the rim of their tires with a 2D nanomaterial ink, and indeed we managed to improve heat transfer of about 1,000 times. And this technology is now running in Formula One since about 5 years. So we're quite happy with that. Last but not least, Kenwood JVC asked us to embed 2D nanomaterials for their loudspeaker and woofer smart membranes. And this is exactly what we have done for a much cleaner dissipation of the sound. So this is just in a snapshot showing you the amazing things and the numerous types of things you can do with 2D nanomaterials inks. I think you have some extremely important advantages that we love, and the fact that we have so many different 2D materials to choose from, the easiness of handling them, and the added value of processing them in liquid really makes us all these processing techniques based on printing or film depositions super easy, and really push the performance and really overcome a lot of problems that otherwise would have been impossible to overcome. So with that, I would like to thank the people who actually do the work in my lab and have done all the work that I've showed you today. I would like to thank my collaborators, John Coleman and Stefano Sanvito at Trinity College, Clotilde Cucinotte and Felice Torrisi at Imperial College London, staff Van der Toulouse, Sandra Van Hert and their group in Antwerp for the microscopy, Yuri Gagozzi and his team at Drexel, and Quentin Ramaz at SupStem, and last but not least, the funding. And I would like to thank you all again for the nice invite and give me the chance to tell you about my research. Thank you.
Thank you so much for the wonderful talk. I really enjoyed it. And we have some time now for questions. I see one question has already been added to the chat, so I'm going to read it. Does the protective layer on exfoliated black phosphorus formed by solvent evaporation affect the electronic properties of the material?
No, the nice thing actually that we have seen is that it doesn't affect the electronic properties of the material. We have tried STM, STS, and it's actually pristine. So we are quite happy with that actually.
Okay, then the second part of the question is obsolete. I'll continue because I have a question obviously about your Maxine work. I see that you have studied a carbonitride Maxine. Maybe I missed it, but how good of an idea do you have of the carbon to nitrogen ratio in the carbonitride?
That's a very good question. We haven't quantified it. We haven't done any quantification. All we know is that I mean, from batch to batch, it doesn't vary. So we have consistency. And it doesn't get changed when we process the material. So as from going from exfoliation to ink preparation and then processing, this is for us the main worry, that we don't really damage the material by laying it down. Some of the deposition techniques are a little bit more aggressive than others. For example, inkjet is quite mild. The extrusion printing is quite mild, but when we do the 3D printing, we do use an aerosol jet printing technique, and there you actually sonicate quite heavily the dispersion while you print it down. And again, we do not see any change in the structure. We have tracked it before and after, so we haven't quantified the ratios there, the actual stoichiometry, but we are confident that we are not damaging it.
Okay, yeah, we have some max phases, carbon nitride max phases, and we're it's giving us quite the challenge to to determine exactly how much carbon to nitrogen we have.
Definitely.
So okay, thank you. So the next question that I'm seeing in the chat is, have you tried other materials than copper to make wires in the black phosphorus? My first thought is creating phosphorus nitrogen junction on a nanowire scale.
Very, very good thought, Justin, I think is your name.
Yes, exactly.
Definitely a very good question. So what we have tried, so the amazing thing about copper is that it forms very, very easily. We have tried platinum, we have tried gold, we have tried silver, we have tried many other, and I have to say that I think it's probably a kinetics issue. So we're still studying the kinetics, but so far we haven't seen it being made with any other element, with any other we have tried so far. Copper is being super easy, so easy that we didn't expect it at the start.
Okay, Ankit, you have a question, go ahead.
Yes. So very nice talk, very fascinated to see all these devices being print. Very nice, very impressive. So I was just curious about if there is any study on long-term performance of these devices, particularly because when we are talking of these devices which are approaching the nanoscale dimension, microscale dimension, we have effects like thermomigration, electromigration, backstress formation in these devices. So is there like a really long-term study on how effective these are?
We have done studies up to months. We haven't done any study beyond, I think the longest study we did was 6 months looking at the same device, and we didn't see any appreciable degradation. Having said that, we are pursuing that for we're doing some more systematic studies for the devices printed on textiles. Most likely, actually, the reason why we're doing that is because there we're also adding washing and things like that, washability studies. And in that case, we have improved quite substantially the performance, the length and the shelf life of the devices by using a capping layer, basically, a transparent capping film. So in that case, even if you were to see in the conventional devices some sort of degradation, the other way would be just to cap them and kind of work around that as a solution. But for the conventional devices printed on PET or whatever other substrate we have printed, we haven't seen any appreciable degradation of performance within 6 months. Okay. Beyond that, we haven't tested.
Okay, yeah, thank you.
Okay, moving on, there's another longer question in the chat. For the heat dissipation problem in the Formula 1 racing wheel, what was the thermal conductivity of your material? And what is the temperature of the wheel with and without your material?
So the thermal conductivity of the material, I cannot say, because it's one of the things I cannot say, because otherwise you might know what material was, and then I get in trouble. The temperature, actually, it gets extremely high. Really, I think we're talking about, above 400 degrees C that it actually gets. So this is, and again, it was a very, very simple solution for us it's one of the most common 2D materials that we used. We didn't use graphene, but it's probably the second most common material that worked out well. Yeah, that's all I can say.
Okay. That's great. Peter, you have a question? Please go ahead.
Valeria, thanks for the very nice talk. I enjoyed it. I had a fundamental question, and you may have said this and I missed it, about the copper nanowire. So they grow along, I think, the 010 direction. And my question was, I mean, that surface is periodic. So my question is, why don't you get a copper sheet? What determines the actual diffusion pathway along a particular row of the phosphorus?
This is an excellent question, Peter. In fact, I probably didn't come across, actually, probably didn't stress it. The beautiful thing, actually, about the structures is that actually they don't grow as 2D wires, right? Or 1D wire. Actually, if you do cross sections, it goes in the deep in the thickness of the 2D material of the black phosphorus. So actually,
it's like the steps along the step edges.
You form a sort of wall along that direction, not a single wire. It just goes into the thickness. As you saw, when we do liquid phase exfoliation on black phosphorus, we don't get mono layers, or we get very few of them. Most of them are around 8 to 10 layers. Right. And these copper structures go all the way down.
Huh, interesting. Wow.
Yeah, it's fascinating. It's really fascinating. It took us, not underestimated, about 2 years to understand what was going on there.
Interesting.
So Christina,
thank you. Thanks.
Christina, I have a question.
Yep. Go ahead, Krishna. Yep.
So I'm a bit, this is just my ignorance. What is the source of copper? Because I thought that you were sprinkling copper nanoparticles, and now the dimensions of the copper in there is smaller than the size of the nanoparticles, right? So
yeah, it was. So I'll tell you. So initially, if you don't do microscopy, you might not be familiar with that. So the support grid that we normally use, you have a carbon grid, and then you have a layer of a carbon-based material, polycarbon, and then you drop cast there. So what we found at the start is a very unusual finding, was that when those flakes that touched the copper grid, as opposed to they were just straight from on the grid, from the copper, we observed in this case this hot behavior of this huge number of lines starting there. So what we did was we changed the grid. We went away from copper. We bought, I think it was a platinum based, a different type of support grid, and we sprinkled copper nanoparticles that we bought on it. And then again, we saw that the wires were forming starting from these nanoparticles. So it was copper that was exactly what we were saying before with Peter, diffusing along these grooves of the black phosphorus. So that gave us really, that together with the eels, really told us what was going on in a way, not understanding what the structure was, but actually pinning down the system where it was happening and how it was happening. So it was really we finalized the thing that it was really from the copper. It was the copper that from the grid was migrating and diffusing along the grooves of the black phosphorus to form this sort of, as Peter said, these sheets or these walls across the thickness of the flakes. It was quite fascinating.
So what was what is the driving force? I mean, is there an electrostatic minimum in the grooves that drive that, or?
I think so. I think it might be. It might be that, yeah.
Because you do see some of it when you grow graphene on any of the copper, because there are ripples in the graphene that you also see these effects. Okay.
But probably in that case, you never see such an order type of structure that forms, mostly because the graphene doesn't have that sort of atomic structure that drives this growth.
Okay, that's
yeah.
So do I have, Christina, one very quick question? So in the MXene's edges, right, when you dissolve it or exfoliate it in water, typically what's the thickness of your?
Oh, the MXenes, they are down to mono bilayers. They're really, really thin.
Oh, really? So it's
the exfoliation is so much more efficient than with van der Waals crystals.
Yeah. Wow.
Yeah.
And do you see what are the functional groups at the edges? I mean,
you have all sorts of things, OH group, fluoride groups, and it's a collection of all different types of functionalities. And these again add complications because they make it so damageable. They're very prone to oxidation and degradation, but at the same time I think opens up a lot of possibilities around functionalizations and things like this. So it's a whole new Pandora box there to open.
Is it possible to form, like, could you cross-link them and form gels? Because that's been done with graphene oxide.
This is a good question. I don't see why not, actually. The functional groups are there.
Yeah, okay.
This is a very good idea. The functional groups are certainly there.
Okay, cool. I know this is really interesting. Hope when you visit Phoenix, you can also visit Tucson.
Absolutely.
I see another question in the chat. What is the skin depth of your material for EMI shielding?
The skin depth, I'm not entirely sure. It really depends on a lot of things. We have tried a lot of things. I'm not entirely sure what's the actual skin depth.
Okay, that makes it easy to move on. And Bruno, go ahead, please. You have a question?
I like how Christina says my name, Bruno.
Are you making fun of my German accent now? That's
Valeria, it was a fantastic talk. I spent a lot of time thinking about a question, and sometimes it's about things you haven't done yet. But one of the things that I was very curious is you were if I'm correctly, we're taking those porous ceramic precasts and you were imbibiting the inks inside of them, right?
Yes. Yeah.
And what are there challenges with imbibition in the sense that the flake size is in a comparable range with the pore size of the material? Are there any constraints there for the material?
We haven't found any constraint there, because actually the MXenes beautifully coat these structures, regardless which size or which. I mean, we have tried. There are ways of selecting sizes in MXenes. So we have tried with large sheets, with medium sheets, and smaller sheets of a few hundred nanometers, and you always get a beautiful coverage. The challenge there is in how brittle this device is, the freestanding object is. So at the start, it was a nightmare to learn how to pick them with tweezers, or they were flying away. They are basically all air. So it was extremely hard to handle. So that's why we started to make shapes and things that were much bigger and easier to handle. But no, the coverage is really efficient, and all you need to do is just dipping these ceramic templates into the ink, and all you get, literally, you dip, and after a few seconds is all black.
Wonderful.
Yeah.
Okay, do we have more questions?
I can have one more question.
Yeah, sure, go ahead.
Have you thought or have any interest in working with this imbibition when you do that into, instead of a ceramic, have you thought about doing this into like porous metals and metallic foams?
Yeah, yeah, we haven't thought about doing it actually. Again, the reason why we did on the ceramics is because these ceramics, they make tetrapods, and then the tetrapods really are the ones that then leave this cylindrical hollow type of structure when you etch them away. But having said that, there shouldn't be any reason why we couldn't try your suggestion. Certainly, we haven't tried. This was for us a very nice and easy entry level, but certainly.
And what was the pore size on the ceramics?
Oh, and the pore size we get is about 10 nanometers, 15 nanometers. It's, yeah.
Supposedly the sheets have to kind of curl.
The curl, and they just wrap them around, yeah.
Like this must be a really interesting, like a swimming almost kind of
yeah
scenario. Very interesting. I didn't. Wow.
Yeah, it's fascinating, and you can do them with. You can do the very same type of systems with graphene oxide. It's yeah, it's quite versatile as a method. Yeah.
I wish I could see that happening. Like it must be a beautiful phenomenon.
Yeah, it's.
I see there's one more question, I believe. What are the values for permeability and conductivity for your material for EMI shielding?
So for the EMI shielding, the hydrogels, so the permeability I cannot remember on top of my head. The conductivity we could get about 800 Siemens per centimeter, something like that. Mm-hmm. Not super conductive, but conductive enough to use them as motion sensor, looking at resistivity. Yeah.
Yep. Great. Well, thank you so much. Are there any more questions from the audience? We are approaching, I believe 12:15 Arizona time. Over here, it's like 8:15 p.m., 7:15 in Ireland. So, Peter, are you saying goodbye, or do you have another question?
No, I'm just saying goodbye. Sorry.
Okay.
Thanks, Valeria.
Thank you
very much.
Thank you so much, everybody.
Very nice.
Thanks, everyone. Thank you.
Thanks for the wonderful talk.
Thank you.
Bye.
Bye.
Bye. Bye.